And so there's a lot of stuff going on in here, and it can be a little bit confusing to kind of break it down to see what's really going on. But this here on the left, with those parentheses, this is a binomial, right? There's a plus sign in there, which means there's one term on the left and a second term on the right. So there are two terms on the left side here, a binomial, right? The prefix bi means two. On the right side, this is another binomial, meaning there are two more terms on the right. And because these parentheses are like right next to each other, it means multiplication. So we're going to be multiplying these two together. And so whenever you multiply something inside of parentheses, you distribute. But because there are two terms out in front of that second set of parentheses, we have to distribute each of those terms separately. So here's what that's going to look like. Starting off by taking this first term, the 5 square root of 2x. So I'm going to take it and multiply it by that first term, and then multiply with that second term. And whenever we multiply radicals together, we multiply those coefficients first, like the numbers out in front of the radical, they get multiplied together first. So in this case, it'd be like this 5 times the negative 4, which gives us negative 20. And then we multiply the square root of 2x times the square root of 2x. Do you remember what happens when you multiply one square root times the same square root? What happens to those radical signs? Do they stick around or do they go away? I'm getting some nods for a response. I'm assuming you all are nodding. Yes, they go away, right? Yeah. Like the square root of 2x times the square root of 2x would just be 2x. Because it's really saying like, yeah, the square root of 2x squared in a way. And so like the square and the square root cancel out and they leave us with just the 2x. Because those are opposite operations. So when I multiply root 2x times root 2x, you get just 2x. And that's true for any square roots, right? The square root of 10 times the square root of 10 is just 10. All right, so now when I distribute it to that second term on the right, you have the 5 times, well, there's nothing in front of that second radical. So that 5 is just going to come along for the ride. But then the square root of 2x times the square root of 5x. So those are both square roots, so we can multiply them. And then you multiply the numbers together, right? The 2 times 5 to get 10. And then x times x is x squared. Are we going to be able to simplify that, the square root of the x squared? We'll do that in the next step. So that's distributing this first term from out in front, the 5 square root of 2x. Now we're going to distribute the second term that's out in front. And we're going to do that same exact process, distribute it to each term in the polynomial on the right. So first, we have square root of 5 times this negative 4 root 2x. Well, there's no number in front of the square root of 5, so it's just going to keep that negative 4. And then the square root of 5 times the square root of 2x. Well, we're just going to really multiply like the 5 and the 2. The x just comes along for the ride. So this is the square root of 10x. And then finally, we're going to take this and distribute it to that last term. So square root of 5 times the square root of 5x is positive square root of, well, 5 times 5 is 25. And then that x. So after multiplying these two together and distributing them, we're going to have these 4 terms. Our next step will be to simplify each one of these if we can. They won't always be able to, but some of them we can still simplify further, do a few more calculations. Like this first term, for example, this is just multiplication. So we can take negative 20 times 2x. That's just going to be a negative 40x. For the second term, that blue one up there, you have 5 times the square root of 10x squared. So I can't simplify the square root of 10. That doesn't break down further. 2 times 5, there's no groups of 2. But x squared, we can simplify that. We know that the square root of x squared is just x. And so this x is going to kind of escape that radical, right? I can make one group of 2. And so that 1x is going to come out in front, right next to the 5. So this will be plus 5x. And the 10 is still stuck underneath that radical. That green term, the third one up there, negative 4 square root of 10x. Well, looking at that radical, I've got the square root of 10 and the square root of x. Neither of those can be broken down at all. So that one's going to stay put just like this. Negative 4 square root of 10x. And in that last term, that purple one, can I simplify anything inside of there? Square root of 25 is just a 5. So the 5 escapes, can't do anything with the square root of x, so that x stays underneath the radical. And now we look at these 4 terms. Each one of them has been simplified. Now let's see if, are there any like terms that we can combine? What do you think? Just give me a yes or a no. All right, you have very minimal communication you need to do this morning. I know it's early. So yes, can I combine some things, or no, they're all different? What do you think, yes or no? Yes? Yes? Which ones can I combine? They're close though, aren't they? But since this is the root 10 and this is the root 10x, they're actually different terms, which is so frustrating. So like, oh, come on, I want to combine something, but we actually can't. Look, even this one's different, right? That's just the square root of x. And this first one doesn't have any root. So every one of those is actually a different term, which is a little frustrating, but it also makes it easier because that means we're done at this step, right? There's nothing else we can do. This here is fully simplified. All right, so that's multiplying with radicals. And we did a little simplifying. Nothing too major. But today we're going to learn a new operation, and that is division. Ooh. Good news. We don't really divide by a radical. You know, if I give you a birthday cake and I say, hey, split this up in the square root of 10 pieces, or 10x pieces or whatever, you're not going to actually take out your square root of 10x knife and slice it up appropriately. That's ridiculous, Wojcik. Why do you even suggest such a silly thing? So the whole idea behind dividing is basically if you've got something like 2 over the square root of x. Technically, a fraction indicates division, right? Like if you have 3/4 as a fraction, that means you're taking 3 and dividing it by 4. So like that fraction up there, 2 over the square root of x, is technically saying take 2 items and divide it by whatever the square root of x is. So those fractions, that fraction bar indicates division. But in math, we don't actually divide this out and get like a new number. Instead, we just have a certain rule that we have to keep straight for writing. All we need to do is remove any radicals from the denominator. So what this is saying is whenever I've got a fraction, if I'm fully simplifying it, we just have to make sure that there are no radicals, none of those root signs on the bottom. So I just have to get rid of the square root, or if it's a cube root, or even an 1/8 root, whatever that root is. We're just trying to move it out of the denominator and up into the numerator spot. And so this process is called rationalizing the denominator. It's making sure the denominator is rational. Meaning it doesn't have any type of a root in the bottom, because those are tough to divide by. And so we're going to look at a few different cases this morning of different types of radicals that we could have in the denominator, and we're going to look at how we get rid of them. All right, so we're not so much dividing as just canceling out radicals in the denominator. All right, we ready to rock and roll? Okay. So there are two possibilities that I'm going to show you this year in the denominator. There could be a monomial, meaning just like a single term in the bottom, or there could be a binomial, meaning there could be two terms in the bottom with radicals. And to start things off, we're going to look at just a monomial. So if there's a single term on the bottom of a fraction and there's a root, there's a radical somewhere, these are the 4 steps that we have to take. So go ahead, take a minute to jot these down because we're going to be referring to them as we work through our different examples today. So the first 2 steps are just looking at the denominator, which is going to have a root of some type in it. And we need to identify 2 things. First, what's the index, meaning like what's that little number up there? Is it a 3? Is it a 2? Is it a 8? Then step 2 is find the exponent of each base. Right? So here there are 2 separate bases. The 2 and the x are separated, right? That exponent of a 4 is only on the x. The 2 technically has got an exponent of a 1. All right, so you're looking at all the exponents and comparing them to that index. And then I kind of grouped steps 3 and 4 together because it's kind of happening at the same time. Essentially, you want to make each exponent. So you look at every exponent of all those bases underneath the radical. And you want to make it a number that's going to be essentially divisible by the 3. So like here, I've got 2 to the first power. In order to cancel out that cube root, I've got 1, 2. I'm going to need 2 more of them, so I have a total of 3 of them. X to the 4th, well, I could add 2 more of those to make it 6, because 6 is divisible by 3, essentially. I can make 2 groups of 3 that way. And again, we're going to do some examples to kind of illustrate this to you a bit more clearly. But that's the general idea here. We're going to multiply by that root so that the radicals cancel out. Similar to like in the warm-up, when we had the square root of 2x and the square root of 2x, the square roots canceled out, and we're left with just a 2x. That's kind of the idea that we're going to use here to get rid of or remove these radicals. So here we go. Here's a first situation. It's nice and easy. 6 divided by the square root of 5. These are the types of problems you're going to hope for on the test, right? Nice and basic. So 6 over the square root of 5. And first, we need to identify the index of the root. Now, this is called a square root. right here because there's no like index, there's no number up there. Do you remember what number we're supposed to use though if there isn't an actual index written? What kind of a root is that? Yeah, we call that a square root. You know, if like a number is squared, like x squared, does that mean an exponent of a 2? So a square root actually means that we've got an index of 2. We just don't write it in because that's like the most commonly used type of radical, a square root. So this is a square root of 5. And technically, what's the exponent on that 5? That's 5 to what power? Just the first, right? This is like 5 to the first power. And so in order for that radical to like cancel out, I need the exponent on that 5 to be the same as the index. So how many more 5s do I need to multiply by to get it to be a 2? I know this is tricky. If I've got one thing and I need 2 things, how many more things do I need? Come on. You can just use your fingers, everyone. Just hold it up with your hand. Just how many more 5s do I need to get 2 of them? Oh my gosh. What's 2 minus 1, everybody? How about that? Yes. Okay, I saw one person put up a single digit. So I'm going to assume that means everybody knows that I would need one more 5. Because 5 times 5 is 5 to the second power. So that would make it its exponent a 2, which is the same as the index. And that's kind of what I'm looking for. Now, whenever you're multiplying like the denominator of a fraction, whatever you multiply in the bottom, to keep things equivalent, we must multiply the numerator by that same amount. Because like what I have written up there in blue, the square root of 5 divided by the square root of 5, doesn't that just equal 1? And if you multiply something by 1, it doesn't change its value. So we're allowed to do that as long as I multiply the numerator and denominator by the same amount. Now, why on earth would we do this? Well, up top, you just get something different. 6 times the square root of 5. That part's nice and easy. But the bottom is what really matters. So here's what's going on. If I take the square root of 5 times another square root of 5, that equals the square root of 5 squared, right? 5 times 5, we could write that as 5 squared. Now, this is great because remember, this index is technically a 2 because it's a square root. And because the index matches the exponent, they cancel out and we're left with just a regular old 5. Or another way to think of it is that's the square root of 25. And we all know the square root of 25 is just 5. So there's no more root in that denominator. It is canceled out and we're left with just a regular old-fashioned 5. So at this point, we no longer have a radical in the denominator, meaning we did what we wanted to do. We have rationalized the denominator. We got rid of any radicals on the bottom. It's fine if we have them up top, you just can't be dividing by a radical. And so it's kind of weird because we didn't actually do any division, but this is technically what's called dividing by a radical. You're just getting rid of that root in the bottom. All right, let's try another one. Here's a good illustration of this concept. So you have 6x divided by the 5th root of x to the 3rd. So the index of the root is a 5. Currently, I have 3 x's under that root. In order for them to cancel out, how many more x's do we need in the bottom? All right, come on, I need to see some fingers. Awesome. Okay, this is getting better. Just hold up. How many more x's do we need to cancel it out? Awesome. Good, good, good. It's like half the class now participating. This is wonderful. Thank you. So if I've got 3 x's, to get to 5, I need 2 more of them. So I'm going to multiply by, it's got to be the exact same type of a root, right? You can only multiply like radicals, so it's got to be another 5th root. But underneath here, I'm going to multiply by x squared, because when I multiply x to the 3rd, times x to the second. That gives me a total of 5 x's that are being multiplied together. And that's what I'm looking for because that's the index. I have to multiply the numerator by that exact same amount. So the 5th root of x squared. Now, in the numerator, for a fraction, you just multiply across the top. There's nothing you really do here. You just push those two things together. So I've got a 6x times a 5th root of x squared. Right? There's no actual calculation you have to do there. That's the nice and easy part. But here's where we see the magic happen. When I'm multiplying these two 5th roots, I'm going to get another 5th root. Right, because that's the same index. But if I multiply x to the 3rd times x to the 2nd, that gives us x to the 5th. When you multiply the same base, you add the exponents up. 3 plus 2 is 5. And so looking at this radical down here, see how the index and the exponent are the same now? They're both like a 5. So the 5th root of x to the 5th, essentially it's saying, hey, if I've got 5 x's, how many groups of 5 can I make? Well, you can make 1. So it's like those 5 x's escape outside the radical, if you remember my concept from last week on how to simplify these. So the index and the exponent cancel out, and they leave us with just a regular old x. So that x is our denominator. We no longer have any radical in the denominator, which is awesome. That's what we wanted. But now looking at what I've got written up here in the green and red, is there something else we can still do to simplify that fraction further? Do you see something that's the same on the top and on the bottom? Yeah. There's an x up top and an x on bottom. We know that anything divided by itself equals 1. So we could just cancel those out. And we'd write our final answer as just 6 times the 5th root of x squared. And so that would be that simplified fraction. Does that problem help make it a little bit clearer as to like what our goal is, what we're trying to do? If I hear no objections, I'm going to assume that that's a resounding yes from everybody. But seriously, any questions on these steps yet? Or kind of feeling okay with it? Don't worry, we have some more. All right, so we got 4y divided by the 4th root of 2y squared. Okay, so looking at that denominator, we look at the index of the root, and there's a 4. So that's kind of our focus. I need to get everything under that radical to have like an exponent of a 4 or a multiple of 4. Now here's where you have to be careful. A lot of students will just look at that y squared and ignore the 2. But we have to remember that 2 is its own separate base. This is technically 2 raised to the 1st power. All right, so we have to cancel out the root above the 2 and the root above the y. So we've got to think about both of those exponents. So we're going to multiply by a 4th root of 2 to some power and y to some power. All right, and for both of them separately, we have to think about how many more 2's do I need to get to a 4, and then how many more y's do I need to get that up to a 4. All right, so hand signal time. How many more 2's do we need, everybody? Okay, 3 more. Right, I have 1, 2. I need 3 more 2's to get it up to a 4, because then that'll be 2 to the 4th power, which matches that index. How about the y's? How many more y's are we going to need to cancel out? 2 more, right? I've got y squared. We need to multiply by another y squared to make it y to the 4th power. Then its exponent will be the same as that index, and we just cancel those out. So up top, we also have to multiply by the 4th root of 2 to the 3rd times y to the 2nd. Let me move this. In our numerator, up top, that's the easy calculation. We just kind of write everything next to each other. 4y times the 4th root of, and I can leave that 2 to the 3rd power. I could leave that as 2 to the 3rd, but sometimes it's nicer to multiply it out, right? 2 times 2 times 2 just gives us 8. So that'd be 8y squared. Now let's think about what's going to happen in our denominator here. So we're multiplying these two 4th roots. When we take 2 to the 1st times 2 to the 3rd, that's going to equal 2 to the 4th, because you add up their exponents. 1 plus 3 is 4. Y squared times y squared is y to the 4th. So do you see why we chose those numbers, how those exponents both match the index now? And so the 4th root of anything to the 4th, well, that index and those exponents cancel each other out. The 4th root of 2 to the 4th is just 2. The 4th root of y to the 4th is just y. And so this whole term here just equals a regular 2y. And that's going to be our denominator, 2y. Can I simplify anything further? If I look at that fraction, look at the numerator and denominator, are there some things that can cancel out or simplify? Yeah, so look at those coefficients first. I have 4 over 2. Well, 4 divided by 2 is just 2. The next one, I've got y over y. Those would also just cancel out. Anything divided by itself equals 1. And then all we're left with is this root, the 4th root of 8y squared. And I can't break that radical down anymore because 8 is only 2 times 2 times 2, right? I only have 3 2's. And I only have 2 y's. And because the index is a 4, I would need 4 of a kind to like escape the radical and move out in front. So these are simplified completely. 2 4th root of 8y squared. Questions yet on anything, any little part of this? Okay. All right, we're doing all right. I have one more case. So now I've got a radical over an entire fraction. This looks a little weird. Whenever you're taking any type of a root of a fraction, you're able to simplify it or just to like rewrite it as taking the root of the numerator and then the root of the denominator separately. So it's like I'm going to take the root of each of those instead of like the root of the whole thing. It's the same thing. So I'm going to rewrite this as just the cube root of 9 over the cube root of x to the 4th. So whenever you have a fraction with the root, just take the root of the numerator and then take that same root of the denominator. And now we can think about taking each of those roots separately. It's almost like you're distributing the radical in a way to the numerator and to the denominator. So up top in the numerator, cube root of 9, we actually can't simplify that, because if I broke the 9 down to 3 times 3, that's only 2 3s, and I would need 3 of them to cancel out because it's a third root or a cube root. But in the bottom, index is a 3, and I currently have a 4. So this is different because I have more than the index right now. So to cancel it out, I need to multiply by some additional x's so that its exponent is divisible by 3. All right, so 4, is that divisible by 3? Just give me a yes or no. No. All right, so if I go up by 1, is 5 divisible by 3? No. Is 6 divisible by 3? Yeah. So if this were x to the 6th, we'd be in business. So that should be our next goal. We want to get that exponent to be some number that's divisible by the index. Well, in this case, that would be a 6. So to make that an x to the 6th power, how many more x's do we need to multiply by? You're going to show me with your fingers. How many more x's do we need? 2. Awesome. So I'm going to multiply by the cube root of x to the 2nd. And let's take a look at what's actually going to happen here. First off, we multiply the numerator by that, cube root of x to the 2nd as well. But here's where the interesting stuff happens. Look at these denominators. This becomes the cube root of x to the 6th power now, right? Because x to the 4th times x to the 2nd gives us a total of 6 x's that are being multiplied together. So I'm taking the cube root of x to the 6th. Now, if you think about this, we're multiplying 6 x's together, and that index is a 3. So it's really looking at, hey, how many groups of 3 can we make? Well, there's one group of 3, and there's another group of 3. So how many groups of 3 can we make? 2. So this time, it's going to change not just to an x by itself, but to an x squared. Essentially, you take the exponent and divide it by the index. 6 divided by 3 is just 2. So this denominator is going to become x squared. Whereas all our other ones was just an x, because we were trying to get the exponent equal to the index. In this case, the exponent was already bigger, so we're going to have additional groups that we can make. In our numerator, since those are both cube roots, we can actually combine it and write it as a single cube root. So this will be the cube root of 9x squared. So at this point, in the upper right corner in green, we no longer have a radical in the bottom. But could I simplify it further? Like, to see that x squared up top and x squared at bottom? Am I allowed to just like cancel those out? You kind of want to. It looks the same, but unfortunately, because that numerator is underneath a radical, it's not the same as a regular x squared, right? That's the cube root of x squared. So it is a different amount. Like if you plugged in a number for x, the cube root of x squared would not be the same as just a regular x squared. And so because of that, they're not like terms, you can't like cancel them out. They're not the same thing. So this is our final simplified answer, just like that. Questions at this point? If anyone at home has any questions, you can ask too. Awesome. So these were all the different types of scenarios you could expect to see when there's a monomial, a single term in the bottom with the radical. The next possibility is, what if there are two terms? Don't worry, I got good news. If there are two terms, if it's a binomial, it's a lot easier. In fact, look at this. To rationalize a binomial, look how many steps there are. Just one step instead of four. Super duper easy. So go ahead and jot this down in your notes. And we're going to be multiplying by something called the conjugate. And I've got a little example and definition of that down at the bottom. I mentioned this at the last example on Thursday, but still, jot down this example and then I'll go over it again. All right, so if there's two terms in the bottom and at least one of them has a radical, we multiply by what's called the conjugate. And the conjugate's a very, very simple concept. So take a look at this. 2x plus square root of 3, 2x minus the square root of 3. These two binomials are conjugates. What's the only difference between them? The sign. Yes, good, that's right. Yeah, the sign is different. This is a plus, that's a minus. So whenever you're trying to figure out, hey, what's the conjugate of this binomial? You take those same exact two terms, but you just change that operation that's in the middle. All right, so if it was a plus, make it a minus. If it was a minus, make it a plus. And that's it. So here we go. 1 divided by 4 plus the square root of 3. Now, some students might be tempted. So first off, don't do what I'm about to do. I'm going to show you what not to do. Don't write this down. Might say, oh, there's a square root of 3. Let's multiply by another square root of 3. Seems feasible, except you have to remember that since there are two terms in the bottom, you'd have to distribute this square root of 3 times both of them. So where the square root of 3 times the square root of 3 is just a 3, when I multiply it by the 4, I'd get 4 square roots of 3. And so by multiplying by just a single square root of 3, did I get rid of the radical in the denominator? Well, I got rid of one of them, but see how I added another one on the other term? So that doesn't work, right? The whole purpose is to get rid of all the radicals in the denominator. That's why we have to multiply by this conjugate. So the conjugate of 4 plus root 3, super simple. It's just going to be 4 minus the square root of 3. And we do that on the top and on the bottom. Now, why does this work? Why is this all of a sudden going to magically get rid of all the radicals? So remember that these are binomials, meaning they're technically in parentheses. They're little two-term polynomials. Up top in the numerator, we're just multiplying by 1, so that just gives us 4 minus the square root of 3. But what happens when we multiply the bottoms together? Well, there's something really special that happens when you multiply two conjugates together. Normally, we'd have to do that whole distributing thing, like we did with our warm-up. Remember, you had like 4 different products that we made. But it turns out, since these are the same terms on both sides, but one's got a plus and one's got a minus, whenever you do multiply, if I have here, when I multiply those two terms, I get 4 square root of 3. When I multiply these two terms, I get negative 4 square root of 3. It's the same term, 4 root 3, but one's positive and one's negative. When you combine them, they just cancel out. So whenever you multiply conjugates together, you don't have to do the full distributing thing because those middle terms will always cancel out, which is great. So this means all we have to multiply, this is just for multiplying conjugates, is we just have to multiply the first terms together, so like 4 times 4, which is 16, and the last terms together, root 3 times negative root 3. Well, positive times a negative is a negative, and root 3 times root 3 is just a 3. Nice and easy, multiplying by conjugates. Now I could simplify it even further, because 16 minus 3, that's just 13. And that's it. Doesn't that seem easier than when it was just one term in the bottom? It's crazy. So 4 minus square root of 3 over 13. So multiplying by a conjugate, again, if you do multiply all 4 of those terms together, that's fine. We'll get the exact same answer of 13. It's just nice to take a little shortcut. If you recognize, hey, conjugate times a conjugate, I don't need to do the full distributing. I can just multiply the first 2 terms together and then the last 2 terms together. All right, and here's our last situation that I'm going to show you for these dividing radicals. So you've got the square root of 2 minus 5, and then the square root of x minus 3. Now these are both binomials. Sometimes it helps to draw parentheses around them to remind you, hey, I have to treat this as a whole grouping together. I can't just focus on like just the root. I have to look at that whole polynomial. And remember, our goal is to cancel out the radicals in the denominator, right? I don't care if there's anything up top, it's just in the bottom. So I need to multiply by the conjugate of the denominator. So instead of a square root of x minus 3, I'm going to multiply by the square root of x plus 3. It's as simple as that. You just change the sign of that bottom term. Make sure you use that exact same binomial on the top and bottom, plus over plus. In the denominator, on the bottom, that's going to be the easy multiplication. Since those are conjugates, I just have to multiply square root of x times the square root of x, which gives us just an x by itself. And then I'm multiplying negative 3 times positive 3. That's also pretty easy. It's just a negative 9. In our numerator, though, we're going to have to do a little bit more work. Are those conjugates in the numerators? No, they're not, unfortunately, which means we do have to multiply all 4 different combinations together, just like our warm-up was today. So we got root 2 times root x, which is root 2x. Root 2 times 3, which we'd write as 3 root 2. Then I distribute the negative 5 times root x, which is just negative 5 root x. So, I mean, this isn't actually that difficult. We're not even multiplying. I'm just putting things next to each other. The negative 5 times 3, here's the only actual multiplication we have, is 5 times 3, which you're all masters of. So that would be our numerator. And looks like we can't simplify any of those roots, and we can't combine any like terms, because every one of them has a different radical. Root 2x, a root 2, a root x, and no radical. So those 4 terms are all different. That's going to be our numerator. And we're going to write this whole thing over x minus 9. So from here, looking at this fraction, is there anything else I could simplify? Anything on the top and the bottom that I could make smaller? The 3 and the 9? Like here? Yeah, 3 and the 9 looks like it simplifies. Also, doesn't like 15 and 9, wouldn't that simplify also? Right, they're both divisible by 3. It looks like we have some options, doesn't it? But, and this is one of the hardest things for students to let go of, we have to remember that this entire numerator is technically all in parentheses. This is a giant polynomial. Our denominator is this entire binomial. They're actually both in parentheses, which means, according to PEMDAS, remember the order of operations, doesn't parentheses always come first? And that fraction line there is division. Well, parentheses definitely comes before division, meaning in order for me to simplify or cancel out, I'd have to perform all those operations in the numerator first. I'd have to, add and subtract these together. I'd get like a single number or something like that. Then I could try to cancel. But because I've got all these variables and everything, we actually can't do that. So I guess the lesson here is we can't cancel out just like part of a polynomial, right? I couldn't simplify like the 15 with the 9 or the 3 with the 9 because they're all part of a bigger polynomial, and you can't cancel out part of a polynomial. Just like as a separate example, if I had something as simple as like x plus 2 divided by x, something like this, we actually couldn't cancel the x's out because I would have to take whatever number x is and add 2 first and then divide it by that x in the bottom. So it's the same kind of concept here. You can't cancel out part of a polynomial. All right, so that's it for the different scenarios that you might see with these radical denominators, but I want you to practice some of them now. So I've got 3 examples for you to try to work through on your own. Remember, this is where the learning comes in. Don't just sit there and wait for me to go over it. I'm giving you time right now to work through each one of these. So go ahead and write down the cube root of 81 divided by the cube root of 9. And I want you to rationalize that denominator. So look at those previous examples that we did. Right, we had 6 different problems. I want you to try to think about, okay, what did I do in this earlier scenario, that earlier example with Mr. Wojcik, and what do I need to do here? I want you to try to apply that process yourself. And this is where the real learning comes in. When you're trying to figure it out for yourself, it's going to help make it click. So just focus on that denominator. It's a monomial. So what were those steps for canceling out a monomial? Look at the index, look at the exponent. So the index in the denominator is a 3. That 9 has an exponent of 1. So how many more 9s will we need to multiply in that denominator? Nice. So that's 9 to the first. To make it its exponent of 3, we would need just 2 more. So we'd multiply by the cube root of 9 squared, because then 9 to the first times 9 to the second would be 9 to the third, and that exponent will match the index. Multiply by that same amount up top, and in our denominator, just to show you what's really happening here, we'd have the cube root of 9 to the third, because you have 9 to the first times 9 to the second, that's 9 to the third. The index and the exponent cancel out, and they leave us with just a regular 9 in the bottom, which is super cool. Now up top, if you did multiply out 9 squared, you get 81. You get 81 times 81, you get some giant number, which is fine. But 81 is not the same as 9 squared, right? Like we always recognize, hey, 81, that's 9 times 9. So technically, I've got 9 squared times 9 squared, which means this is the cube root of 9 to the fourth. Another way that we could write that. And if I have 4 9s, can I make a group of 3? Yeah, I could make one group of 3, couldn't I? So I could actually simplify that numerator further. I could bring 1 9 out in front. I have 1 9 left over underneath the radical. If I had 4 9s, the index is a 3. I can make one group of 3, and there'd be 1 9 left underneath the radical. Does anything else simplify here? Yep, 9 on top, 9 on bottom. We can cross those off. And our final answer is actually just the cube root of 9. So I added in a little extra pizzazz to that numerator for you. But the main concept I wanted you to get was just that denominator, getting rid of the radical in the denominator. So if you didn't recognize that the 81 and times 81 is something that bigger, that's okay. The main thing is, were you able to get a 9 in the bottom without the root? Okay, let's try this one. All right, this one's pretty straightforward. The square root of 5 over 12a. It's just like that one case where you had to kind of separate the square root, right? So make that the square root of the numerator and the square root of the denominator. And so the denominator, you're going to have just a square root of 12a. And remember that the 12 and the a are each their own separate base, right? There's two different bases, the 12 and the a. And think about, well, how do I cancel that out? Think about their exponents and think about the index of that root. So the first thing, you break up the root just like this. Whenever you got the square root of a fraction, take the square root at the top and the square root at the bottom. And your focus is, hey, how do you get rid of this square root of 12a in the denominator? You think about the index, and you think about the exponents. This is an index of a 2. That's 12 to the first, and an a to the first. So how many more 12s do we need, and how many more a's do we need to make it, their exponents, a 2? Well, I've got a 1 of each of them. I just need one more of each of them. And so then the focus here should be to multiply by another square root of 12a to the first, if you want to write those in, 12 to the first and a to the first on the top and bottom. Up top, those are both square roots, so I can multiply those together. 5 times 12 is 60. And my denominator, the square root of 12a times another square root of 12a, is just 12a. The square roots cancel out. Could we simplify that numerator at all? So this goes back to the simplifying radicals in your factor tree. When I see 60, I think about time. Like there's 60 minutes in an hour, and a quarter of an hour is 1/4. That's like 15 minutes. So I could actually break down the square root of 60 as the square root of 4 times the square root of 15. And do we know the square root of 4? It's just 2. So I could rewrite this as 2 root 15. It's a terrible 15. So I can make this 2 square root of 15a over 12a. Am I done? There's one last thing we can simplify, right? Looking at those coefficients, I have 2 over 12. Well, 2 over 12 simplifies to 1 over 6. So the final answer would be the square root of 15a divided by 6a. Did anybody else get this, just out of curiosity? Okay, a couple of you. That's awesome. Got one more for you to try out, okay? All right, this is it. The final division with radicals. And then we get to do our second lesson for the day. What? So this is a binomial on the bottom. And remember, to cancel out a radical with a binomial in the denominator, you multiply by its conjugate. That's that really easy thing where you keep the same two terms, but just do the opposite sign. Only thing you need to worry about is that fourth root of 3. I'll give you a little hint. This is the fourth root of 3 to the first power. That helps you think about what you have to do with that conjugate to get the radical to cancel out. So yeah, you've got the conjugate. But when you multiply the radicals, since this is 3 to the first power, and you want it to be 3 to the fourth, how many more 3's do we need right here? Yeah. Good. Yeah, you've got the right conjugate by flipping the sign. But for the radicals, since this is 3 to the first power, how many more 3's would we need over here so that's the same as that index of a 4? And make that the exponent on that 3. Cool? Yeah. 3. Good job. Good, good. Yeah, perfect. And then just remember for a conjugate, you flip the sign, right? If this is a minus, make this one a plus. But yeah, you got the exponent. How's it going? So what's the conjugate of this? Do you remember what that means? No. So look right here. What do we do here? What's the only thing that we changed? Mm-hmm. Yep, same thing on the top and bottom. And then the only other thing we need to think about with these radicals is this is 3 to the first power. And so this 3, how many more 3's do we need to make it match that index of a 4? Yeah, exactly. So that's the exponent that you need to put on those ones. You got it. Yes. But you got the big concept of what to do. Cool, yeah, that works. Oh, to multiply it out? Yeah, you can multiply it or make it smaller, try to break it down, like with the factor tree kind of a thing. So where'd you get the 18 from? Oops. Good. Got the right step there. Yeah, you got the right idea. All right, I love what I'm seeing. Everyone seems to be visualizing the right concept of what we need to do here. So we want to multiply that denominator by its conjugate, which everyone's catching on to really nicely. Instead of a 2 minus, it's a 2 plus, right? Nice and simple. 4th root of 3. But because these are radicals, we have to think of one additional piece. And that is, I want those radicals to cancel out when they get multiplied together. And since that's 3 to the first power on the left, I need to think, well, how many more 3's do I need in order for them to cancel out? Well, I would need 3 more to make it cancel out with that index of a 4, right? If I had 1, 3, I need 3 more of them to make it 4 altogether. And we multiply this on the top and on the bottom. So 2 plus the 4th root of 3 to the third. And then all of these are in parentheses. And the key thing here, I know you can multiply the numerators together just fine. The key step in the denominator is going to be, because these are conjugates, we're allowed to take a little shortcut and just multiply the first 2 terms together, which is a 4, and then multiply the last 2 terms together. So that's a negative times a positive, so it's going to be a negative in here. And then the 4th root of 3 times the 4th root of 3 to the third would technically become the 4th root of 3 to the 4th. And that's what I wanted. I wanted that exponent to match the index, because when that happens, they cancel out and leave us with just that 3. And that was our focus, that the radicals were gone all the way. So that's a 3 in the denominator. Now up top, because those are not conjugates, we have to multiply everything out, right? Do the super distributing. So first I've got 8 times 2, which is 16. And then we're going to have an 8 times the 4th root of 3 to the 3rd. And then we have 2 times the 4th root of 5. And then, don't even have room for this last piece, 4th root of, well, 5 times 3 to the 3rd. 3 to the 3rd is 81. 81, no, I'm sorry, that's 27. It's a lot easier. 27. And then 27 times 5 would be 135. Is that right, anybody? 5 times 25 is 125. Times 210. Yeah, 135. Anybody else get that? The 4th root of 135? So I'm multiplying this times this. So it's 5 times 3 times 3 times 3. So the final answer, first off, in my denominator, I have 4 minus 3, which is just 1, which is nice. And so I'm left with just 16 plus 8 4th root of 27, because 3 times 3 times 3 is 27, plus 2 4th root of 5, plus 4th root of 135. And all of those terms are different, right? Everyone's got a different radical. So that right there is the final answer. Questions? I see some confusion on faces. Like for this final answer, it's right here. 4 minus 3 equals 1. And same thing, divide by 1. We don't need to write that divided by 1. And so technically, yeah, this whole thing is all over 1, but we don't need to write divide by 1. Other questions? Hey, take a look at this. There's nothing else. Yay! Don't worry, we still have our second lesson for today. Yes! I know, you were all worried, like, what will we do for the next 20 minutes? Just sit here? No, of course not. We have some more